Okay, hello. I'm Felipe. I'm a PhD student at the University of Edinburgh. And I'm presenting this work whose title is Waveform Generation based on signal reshaping for statistical parametric speech synthesis. I'm studying at the CSTR, the Center for Speech and Technology Research. And the authors of this work, well, it's me, Kasia Valentini, Zizhen Wu, and Simon King. So, in order to start, this is like the general framework of statistical parametric speech synthesis, where you put a text that you want to synthesize, and there is a regression model, text processing, that take that text, then this regression model generates some parameters, acoustic parameters, and then there is a stage called waveform generator, which takes these parameters and transforms these parameters into speech. These parameters are usually F0 contour, pitch or pitch of the signal, a periodicities of the signal, or a spectral envelope, okay, which usually is parameterized as an MGC, or is compressed in some way. Okay, so this work is related, or is focused on propose a new waveform generator. Okay, that's the objective. Okay, so the waveform generation usually is made up by vocoders. So there are some paradigms for vocoding, but mainly there are two which are the most widely used. And one is the source filter separation, which has some drawbacks. Like, for example, there is a very strong assumption that the speech is linear time invariant in a certain time within an analysis frame. Also, but we know that the acoustic cavity of the speech, the acoustic cavity of is changing every time there is a GCI or a GOI. So when the vocal fold opens or closes. Also, there are some non-linearities on the vocal tract. So at the end, it's not a linear time invariant system. So it's very difficult to separate source and filter. Also, there are other things that are very difficult to model or to estimate, like the number of zeros or poles of a filter, the vocal tract filter, if that filter is minimum phase or mixed phase, etc. On the other hand, we have harmonic models, which are based, generally speaking, in sinusoids with some randomness in their parameters. Like, for example, adding randomness to the phase of the sinusoids, or adding some random noise to the signal, the pure harmonic signal. So in that way, it looks to sound natural, because speech is not purely harmonic, or it's not a pure harmonic. So, but the problem is that if you add some randomness to the signals, or if you want to characterize a speech with some randomness, you need to capture. We have observed that there is correlation, so there is some dependence between stochastic and deterministic part of speech. Let's say there is some correlation between harmonics and the randomness of speech, and that is not very well modeled or approximated by some implementations. So there are some problems here that we want to improve. We want to get rid of that. So in summary, the motivation for this work is that there are many processes for speech production that we don't understand, or we don't know how to model properly. And so we just make some assumptions, try to approximate some equations, etc. And they're very simplistic, okay, sometimes. Also, the dependence between stochastic and deterministic components is hard to capture. It's very hard to model or to capture the relations that are in between the harmonics and the randomness of speech, or the periodicities of speech. Also, we know that vocal tract filter and source signal are not linearly separable. So we cannot separate it as a linear process. Okay? So at the end, we can summarize this, all of these things in one sentence that is extreme decomposition. We think that maybe we should avoid the composition of speech in order to synthesize. So we have some goals. Well, the first goal is the most important, is avoid unnecessary extreme decomposition. Okay. Also, we want to focus the design to make a good waveform generator rather than a vocoder or speech codec. So we want to work with TTS directly, and not it's not aimed at being a speech codec. Okay. Also, we observed that there is some correlation between the periodicities of speech signals and the F0 contour. So we want to exploit that. That maybe with that we can avoid the use of periodicities, which is a parameter that is typically used in statistical parametric speech synthesis. Okay, so these goals, the question is how we can achieve these goals. And the answer is by using natural speech. Why natural speech? Because from natural speech we can borrow from that phase relations between harmonics, for example, periodicities, vocal tract filter characteristics, correlation between stochastic and deterministic components, source signal, etc. Let's say, so natural speech gives us everything what we need, but we cannot use them directly to synthesize, because obviously we don't have an infinite database to make some kind of unit selection to synthesize everything. So, so what we can do? What we can do, I will explain if this is the proposed method. So the method is summarized in this diagram. So we have the text as an input of the system, utrans usually, and then regression model maps that into acoustic parameters. Maps those that text into acoustic parameters. In this case, we're using just F0 and a spectral envelope. Okay. Usually, the DNN or HMN-based speech synthesis, they generate F0 and a spectral envelope, but the spectral envelope usually is compressed in MGCs. So, the first thing that we do to the parameters generated by the regressor is that we segment the parameters. For example, here we have a pitch contour that give us like a flag when it's unvoiced or when is the speech voiced speech. So we can just segment voiced and separate voiced and unvoiced segments of speech, and then we process all of these segments one by one separately. Okay, we are not doing any framing. We are not chopping the signal frame by frame. We are just taking whole segments. Okay, so for example, the segments, the voiced segments are processed by the left-hand side of this diagram, and the unvoiced segments are processed by the right-hand side of this diagram. Okay, so let's suppose we have, let's start with the voiced segments. So let's suppose we have a voiced, already cut voice segment, which is represented by spectral envelope at F0 generated by the DNN or HMM regressor, and then this the spectral envelope is first of all, I want to explain which we have here, that is a database, okay, of natural speech. Database between quotes, because I will show you that this database is just comprises only one signal, okay, and this signal is just a pure long constant vowel, okay. So I want to play the constant vowel that we use for this system. So the idea idea is to have a very constant voiced vowel or voiced signal with constant spectral envelope, constant pitch, etc. So that is stored in the database, there, the voice database. The main idea of the system is to take this constant vowel and transform that or modify that in order to match the parameters that the DNN or the HMM generated. Okay, so I will explain how it is achieved. So first of all, we take the target spectral envelope, which could be this, okay, generated by a DNN, and that spectral envelope is stretched and shrinked. For example, in this example, is shrinked in time and stretched towards high frequencies, okay? And that is the case when the F0 target, so the F0 generated by the DNN, is lower than the F0 of the constant vowel. So it's like I want to, the underlying signal of this spectral envelope has a lower F0 than the constant vowel. So what I want to do is to make the underlying signals to have the same F0. In order to do that, I take the spectral envelope and I do a time stretching and frequency stretching as well. So if I want to increase the F0, that is equivalent to shrink in time and to stretch in frequency. Okay? Yeah. Next step is once we have the target spectral envelope, we want to compute the log spectral difference. So I take the spectral envelope of the constant vowel, we subtract both the spectral envelopes. I want to emphasize that in this stage, both signals, or both underlying signals, have the same F0. So thanks to that, we can do this process. We can do just to compare, to subtract, and just directly. Then the spectral difference is converted to parameters for a dynamic filter, time-varying filter, which is an MLSA filter. It's a very standard filter in speech processing. And this filter, what it does is trying to modify the formats of the vowel so that they can match the required or the target formats. Okay? So here we have the constant vowel, the signal in time domain, pass through the filter, and then that signal contains the formats and the notches of the target signal, of the target parameters. Okay, and then as a last step of this for the vowel, for the voice segment generation, we have pitch shifting. In the pitch shifting, so we have the signal, and then we want the signal to have the required pitch or the target pitch. So we take, for example, in this example, we have base means the constant vowel. So it's a constant pitch, constant F0, almost constant. And then by sample, by resampling each one of the samples in time domain, we can generate, or we can modify the pitch of the signal to match the target pitch, the target F0. Okay, like this. Okay, also we use, we apply a low-pass filter because the resampling can generate some aliasing. So we apply a low-pass filter, and then we don't sample the signal to remove all aliasing, all of these things. Okay. Now, in the right-hand side, we have this is the regeneration system for unvoiced signals. Okay, it's almost the same, but as unvoiced signals or unvoiced phonemes, they don't have F0. We don't apply any pitch shifting, time stretching, frequency stretching. We just do the filtering part of the what I explained. In the database, we have a constant fricative, like this. Okay, we can have more than one, and then we can select the best one according to some measurement, some distance, like spectral average, something like that. But we can use only one if you want. Then, once we have synthesized the voiced segments and the unvoiced segments, we can we concatenate these segments using overlap and add, common overlap and add. Okay, so that's the description of the whole system. And now I'm going to introduce the experiments that we made. So we created or synthesized two voices, a female voice and a male voice, using a deep neural network-based TTS. We use basic signals. What I mean, the constant vowels are from different speakers to the speakers that we want to synthesize. So they are completely different speakers. And we did some Mostro-like tests. 30 native English speakers, 30 sentences randomly selected per speaker, and the systems under test were, first of all, like a hidden reference, a natural speech, then straight, which is a standard state-of-the-art, is widely used vocoder. SRO, that means is the proposed method with ideal settings. SRGen is the proposed method by using a constant vowel from a speaker of the opposite gender. And then the SRTP is the proposed method by using minimum phase filter instead of linear filter. And the SRNS means the proposed method, but not applying some smoothing that is a detail. It's like a detail that is in the process to improve a bit the quality. But I think there is no time to explain so details. The thing is that we tested these systems in a Mostro-like test, and the results of the experiments are, for female voice, that the proposed method outperforms all of the other methods, either in absolute score and rank score. The test, significance test, the differences are significant in both tests, in absolute and rank. It's better than straight, and also is better than the which is supposed to be the ideal version of the proposed method. For the male voice, it's kind of similar, but the differences are not as high as the previous voice. So again, the SRDP, which is the version that doesn't use linear phase filter, is the best one again, but in absolute score there is no significant difference. There is no, but in the rank score it's significant. Okay, if we compare with the straight. Okay. Okay. So as a conclusion, first of all, we presented a new paradigm to generate waveforms for statistical parametric speech synthesis. Also, the proposed method with the filter in minimum phase or non-linear phase filter was the best. The method tends to be better than straight. The other thing is that this version with the distorted phase yielded better results than the ideal settings. We don't know yet why, but it's something that we have to look at. And also another advantage, we use fewer acoustic parameters than regular vocoders. That regular vocoders use as a minimum 3. They use F0, spectral envelope, and a periodicities. We are not using a periodicities because we are taking from the natural speech. And the future work for this, we want to apply this for voice conversion, hybrid speech synthesis, and also for unit selection to join the smooth the joins of unit selection or of that type of systems. Okay, so I want to show you some samples. Okay, cool. I want to show you some samples. This is the best of the proposed method, and this is straight. So we have some. This is.
I don't see this as any kind of risk. I don't see this as any kind of risk.
And this is straight. Oh, well, there's a typo.
I don't see this as any kind of risk.
So you can hear that it has less fuzziness than straight, at least in this example.
Its claims were met with a mixture of anger and disgust. Its claims were met with a mixture of anger and disgust.
Some of male examples.
Good book informs of what we ought to know. Good book informs of what we ought to know.
The difference is not. I think the difference is more noticeable for female examples.
Round mat will cover the dull spot. Round mat will cover the dull spot.
Which was reflected in the results. Also, I want to add this third column because it's very interesting that if I use as a constant vowel from opposite gender, it sounds pretty similar. For example, here I'm using as a base signal a vowel from a male.
I don't see this as any kind of risk. I don't see this as any kind of risk.
Pretty similar.
Its claims were met with a mixture of anger and disgust. Its claims were met with a mixture of anger and disgust.
Okay, thank you very much.